Okay, the third problem, we assume a mass of 75 kilograms, which is approximately my mass, an acceleration of 5 meters per second squared, and we're kind of thinking in the context of the problem again of you crouch down, jump upward. Okay, so the first question is, what's the net force necessary to achieve that 5 meter per second squared upward acceleration? And that's very straightforward. The net force is equal to the product of the mass and the acceleration. 75 kilogram mass multiplied by the 5 meter per second squared acceleration. And that gives us 375 units are kilograms times meters, numerator, divided by second squared, which is in the denominator. And that gives us a 375 Newton upward force. Now, the problem goes on to state, okay, well, gravity is pulling down with a 730 Newton force. Well, gravity is pulling downward. How much force does gravity exert in the downward direction? Well, gravity accelerates three masses at 9.8 meters per second squared. So if we multiply that acceleration by the 75 kilograms, we get the force exerted by gravity on that 75 kilogram mass, on my 75 kilogram mass, let's say, and we get 730 newtons, roughly. So we have a downward 730 Newton force from gravity. We need a net upward force of 375 newtons. So how much force do I have to exert in order to accelerate upward at 5 meters per second squared, which is what requires 375 Newton force. So gravity's pulling down with 730 newtons. I need a net force of 375 newtons upward. Well, intuitively, I've got to exert enough force to counter gravity, and I've got to exert enough extra force over that to accelerate me upward at 5 meters per second squared. Just standing here, I'm exerting that 730 Newton upward force, or I'd be accelerating downward. I need the extra. So there's a formal way to do this, but we can informally conclude that I'm going to have to exert the 730 newtons that I won't normally exert against gravity and an extra 375, giving me a net force of about 1100 newtons, requiring a net force of 1100 newtons to achieve this upward acceleration. Now, a little more formally, I'm going to say that the net force is 375 newtons, and gravity exerts a force of negative 730 newtons, and the net force is the sum of all the forces. Okay, all the forces acting on me. The only two that are going to be significant here are an applied force and a gravitational force. Applied force being the force that results from my legs pushing downward, and that force is actually then produced by the floor. As the floor is compressed or bent a little bit, it pushes back, and that's what pushes me up. So when I push down with my legs, the floor pushes me up. And the applied force is actually the force of the floor, even though when I'm jumping, I think of myself as applying the force that accelerates me upward. That's not really the case, because I'm applying a force downward. A downward force isn't going to accelerate me upward. It's the floor's response to my downward force that accelerates me upward. Okay, anyhow, net force is the sum of all the forces acting on me. That includes the gravitational force that pulls me down, and the applied force actually exerted by the floor that pushes me up. So F net is gravitational force plus applied force, which means that the applied force is the net force minus the gravitational force. And the net force is 375 newtons. The gravitational force is negative 730 newtons. When I subtract negative 730 newtons from 375 newtons, I get plus 1100 newtons. And that might be a little hard to read. I'm going to fix that real quickly. Okay, still a little cramped, but we can at least read it. F net minus F grav is 375 newtons minus the negative 730 newtons equals 1100 newtons. And this agrees with our intuitive understanding that we need a 730 newton upward force to fight gravity and an extra 375 to get the 5 meter per second squared acceleration.